Okay, so we're going to talk about factoring out a greatest common factor. We'll do a few examples here of this, and hopefully it's not too difficult for you. The big thing that you have to remember is that when I say greatest common factor, I mean the largest number or the largest monomial, think of it that way, that you can divide two or more monomials by. So for instance, let me give you an easy example. Not even written down here. You don't see it on this slide, but if I said the greatest common factor of 9 and 12, well, what's the biggest number you can divide them both by? That would be 3. So that's kind of a key thing that we have to keep in mind, the greatest common factor as we go ahead and do this here. I'm going to do something here real quick. Do you want to view it? No. Okay. So we'll keep going on with this. So let me reset this slide, and let's find some greatest common factors here. Looking at our first example, what I would do is I'd look at the 4 and the 3. Forget about the negative sign for a second, and I ask myself, what's the largest number I can divide those two numbers by? And the answer is 1. So I'm going to put a 1 right there. That's the GCF. And then I have to look at the variables, and I say to myself, this is a silly question, but this is what you ask, do they both have x's? And yes, they both have x's. So I can include an x in my greatest common factor. What's the exponent on that x? Well, I have a 2, and I have a 1, and I always put the smaller one, so I'm going to put a 1. I'm not actually going to write it, but it's there. Now I'm going to start parentheses, and when I start my parentheses, what goes in it is what I have to multiply 1x by to get my two original terms. So this 1x times what gives me 4x squared? Well, that'd be 4x. And 1x times what gives me negative 3x? That would be negative 3. So that would be my answer right there. 1x times the quantity 4x minus 3. I can always check. I can distribute, because we're doing kind of like the reverse of distributing. If I take 1x times 4x, I get 4x squared, and 1x times negative 3, I get negative 3x. So that's a quick check that you can use. All right, let's do another one here. This time I have 3 terms. I have a trinomial, 3 terms. It's actually cubic because of this term right here, degree 3. The largest number I can divide those 3 terms by is 5. And they all have y's, so I'm going to pull out a y, factor out a y. Sometimes I say pull out a y. And the exponent is going to be a 1 because it's the smallest exponent I see. I'm going to start my parentheses. And 5y times what gives me 10y cubed? Well, that would be 2y squared. Right? Remember, this has a 1 and this is a 2. They add up to 3. Plus 4y minus 1. And if you were to distribute the 5y into those parentheses, you would see that we got what we originally started with. Alright, let's look at a couple more examples here, maybe 2. Let's see, let's do number 3. I will do them all, why not? 3, 4, and 5. You can always fast forward if you want to. In number 3, you'll notice that this problem, we don't have a number larger than 1 that we can pull out or factor out, and we don't have a shared variable, so I would say that this cannot be factored. That's how you'd answer that one right there. Can't be factored. Done. Alright, number 4. It looks to me like I could factor out a 4. We have m's everywhere, and the smallest exponent is 2. And we have n's everywhere, and the smallest exponent is 1. So that's our GCF right there. Whoops. Okay, so we have 4m squared n, and we're going to, since we factor out a 4, we have to multiply by negative 3 to get back to negative 12. We need m squared. We don't need an n because we pulled 1 out, and that's all we needed is 1. This is going to look sloppy because I'm going to run off my page. I need a 4 to get to 16. I need an m, and I need 1 n. You should not do this, but I'm going to do it. I need a negative 7 to get to negative 28, and that's it. Okay, so my real answer, let me write it down here because it's going to drive me nuts, is 4m squared n times the quantity, negative 3m squared plus 4mn minus 7. That would be my answer right there. Okay. And one more just like this. Let's see. Out of negative 30, 35, and 20, that's looking like 5 would be the GCF. We can factor out an x, and we can also factor out a y to the 5th power. What would be left? Well, negative 6 to get up to negative 30. We would need an x, and we would need a y squared. Here we'd need a positive 7, and we would need an x. The y, we already have all those because there's a 5, and that's what we have to get to. And plus 4, we don't need anything else. So that'd be our answer. Okay, so we're factoring out a GCF. That's always something that you do. Anytime you factor, you always look for a GCF first, the greatest common factor. And that's why we're starting off with that method, the greatest common factor. Okay, so let's look at one more quick example here. Different type of problem. We're going to skip this. All right, where we're factoring out a common binomial factor. And the example says factor completely. Anytime you're factoring, you want to factor completely. So that's not so much what we're worried about right here, is we want to get a common binomial factor. So here's what I'm going to look at. I'm going to look at this as two different pieces. And a binomial is two terms linked together right here. And I see x minus 3 in both of these pieces, so that's actually my common factor. I want to factor that out. Now, remember, once you pull out a common factor, you start parentheses. So there's the parentheses. And I'm going to do this here. I'm going to scratch out the common factor that we factored out. And what's left is what we put in the parentheses, 7 minus 2x. So that's actually our answer right there. We'd say the quantity x minus 3 times the quantity 7 minus 2x. Okay, over here, if you look at the two pieces, we have t squared plus 4 is what they have in common. If you cross out the t squared plus 4, you have a negative t plus 1. Remember, there's a plus 1 right there, even though you don't see it. That'd be your answer. The quantity t squared plus 4 times the quantity negative t plus 1. Now I'm going to get rid of, maybe this is what we'll do. We'll just get rid of this purple stuff that I put up here. We're going to get rid of this answer to make a little more room for ourselves. I'll erase that too because it looks funny to me. All right, let's focus on just on letter A. Now we already had the answers, but I want to show you something here. I'm going to show you that the answer that we got for letter A is actually equivalent to what the original problem was. So let's go over here with this original problem and let's figure out what it would be worth if I distributed. I'm going to draw arrows to show I'm distributing. I have 7 times x, which is 7x, 7 times negative 3, which is negative 21, and then I have negative 2x times x, which would give me negative 2x squared, and negative 2x times negative 3, which would give me positive 6. Now, if you look at those four terms, I can combine like terms, and I could get negative 2x squared. I'm going to put this in descending order, standard form, plus x, 7x, sorry. Did I miss an x somewhere? 7x minus 21 minus 2x squared plus 6x. Oh, there it is right there. So let me erase that. I knew I missed something. So if we combine 7x and 6x, that's 13x. And then minus 21. I'm just going to circle that here for a second. Now let's go back over to the purple thing that we said was the answer, and let's show that if we multiply these two binomials together, what we said was our answer, we're going to end up with the same thing we got over here in the blue. So I'm going to draw some arrows here. Remember, we have to multiply every term in the first set of parentheses by every term in the second set. So we have x times 7 is 7x, and you'll see this look familiar. X times negative 2x is negative 2x squared. Negative 3 times 7 is negative 21. And negative 3 times negative 2x is positive 6x. Alright, well, I have some like terms. Whoops. We have that. 7x and 6x is plus 13x. And then we have minus 21. And if you look here, that is exactly what we got right here. Same expressions. So it's showing that our answer is equivalent to the original problem, which doesn't necessarily mean that we factored the whole way, but it does mean that we haven't changed the value of our original expression, and so we still have done accurate math, I guess you'd want to say. All right, so that's all we're going to do here for factoring out a GCF. Remember, you can always rewind the video or pause it and do whatever you need to do to catch things that you might have missed the first time you watched it. All right, we are done.